To embark on a journey through the era of the largest carnivorous dinosaurs, it's crucial to first immerse ourselves in the landscape and living conditions that shaped these formidable creatures. The age of dinosaurs, a vast expanse of time spanning roughly 180 million years, stretches across the Triassic, Jurassic, and Cretaceous periods, roughly from 250 million to 66 million years ago. During this grand stretch of geological history, Earth's environments were dynamic and diverse, constantly shifting in ways that profoundly impacted the flourishing and evolution of dinosaurs. Imagine an Earth almost unrecognizable from today. No sprawling cities or tangled highways, no modern forests with towering angiosperms or flowering plants as we know them. Instead, much of the land was dotted with primitive coniferous forests, cycads, ginkgos, and ferns. These plants formed the backdrop for some of the most dramatic and intense ecosystems that ever existed. The continents themselves were not arranged as they are now. At the dawn of the Triassic, all major land masses were fused into a single supercontinent known as Pangaea. This massive landmass stretched across the equator, creating an immense terrestrial environment where early dinosaurs and their contemporaries gradually began to take hold. The formation of Pangaea affected climate patterns significantly. With a supercontinent of such size, the interior regions experienced extreme temperature fluctuations, scorching hot summers and frigid winters, because moist oceanic air couldn't easily penetrate far inland. As a result, early dinosaur habitats ranged from arid deserts to lush coastal zones, and these habitats influenced the trajectory of evolution. As time pressed on through the Jurassic and into the Cretaceous, Pangaea began breaking apart, leading to the formation of new oceans and seas and the movement of continents toward their modern positions. This continental drift opened isolated ecological niches and created geographic barriers which helped drive speciation, the emergence of new species, by splitting populations and evolving them separately. Imagine vast shallow seas creeping onto continents, changing coastlines, and creating rich environments abounding with fish, reptiles, and plants. This division also led to different dinosaur faunas on separate land masses. For example, the dinosaurs thriving in what is now North America were sometimes quite different from those in South America, Africa, or Asia due to these geographical separations. Climate during the age of dinosaurs was generally warmer than modern times, with no polar ice caps and higher average global temperatures. This warmth supported lush vegetation even at higher latitudes, allowing dinosaurs to inhabit regions that would now be considered frigid. The atmospheric composition was different, too. Oxygen levels fluctuated through these periods, and carbon dioxide concentrations were often higher than today, possibly helping plants to grow more rapidly and supporting higher levels of herbivorous dinosaur biomass, which in turn could sustain large carnivores. In these settings, dinosaurs evolved diverse lifestyles and adaptations. The ecosystems housed sprawling conifer forests, fern-covered floodplains, river deltas, and expansive deserts. Lakes and inland seas teemed with fish, small reptiles, and primitive amphibians, while the skies above were home to flying reptiles like pterosaurs. These varied environments presented a tapestry of challenges and opportunities that shaped dinosaur evolution, including those of the largest carnivorous kinds. Predatory dinosaurs depended on abundant prey, which in turn depended on vegetation and favorable climate conditions. The interplay between flora and fauna in these periods was a delicate balance. Shifts in the environment could ripple through food chains. With changing sea levels, volcanic activity, and shifting continents constantly altering habitats, the ecosystems were in a state of flux. Such environmental pressures contributed to natural selection and the emergence of ever larger predators as a response to resource abundance and competition. The Age of Dinosaurs also saw dramatic events that punctuated these long epochs: mass extinctions, volcanic supereruptions, and asteroid impacts that repeatedly reshaped life's course. These events often disrupted ecosystems, but ironically, they also opened the door for new evolutionary lineages to rise, including giants among the carnivores. As we ponder the colossal meat-eaters that roamed these ancient lands, it's important to understand how Earth's fluctuating environments crafted a stage that could support such giants. Vast floodplains rich in herbivores, warming global climates, and extensive geographic isolation fostered the emergence of unique carnivorous lineages that rivaled each other in size and ferocity. From scorching deserts where early prototheropods hunted small prey to sprawling floodplains where massive Allosaurus and Carcharodontosaurids ruled, and then to lush Cretaceous landscapes dominated by Tyrannosaurs and Spinosaurids, the evolving Earth was more than just a backdrop. It was an active player in the saga of these prehistoric giants. This awareness of our planet's changing face during the Mesozoic sets the foundation for a deeper investigation into the giants themselves. Understanding the environmental context helps us appreciate not only their incredible adaptations, but also the powerful forces of evolution and extinction that defined their existence. Next, we will delve into how paleontologists define and measure the biggest carnivorous dinosaurs, a surprisingly complex task involving multiple criteria beyond just length or height. This foundational knowledge will prepare us to appreciate the sheer scale and diversity of these apex predators across different periods and continents. But for now, let us linger a moment longer in the dawn of deep time, feeling the pulse of ancient Earth, a world endlessly transforming, yet mysteriously familiar in its rhythms, the timeless cradle from which the titans of prehistory emerged. As we leave behind the dynamic backdrop of Earth's changing landscapes during the Age of Dinosaurs, we venture now into a fascinating and nuanced exploration. How do scientists actually define and measure the biggest carnivorous dinosaurs? At first glance, the concept might seem straightforward. The largest means the longest or the heaviest. Yet paleontology, the study of ancient life through fossils, reveals that measuring prehistoric giants is far from simple. Various factors, some obvious, others more subtle, play a role in understanding these colossal creatures, and the methods used illuminate how scientists carefully reconstruct the true scale and nature of dinosaurs. When we talk about the biggest carnivorous dinosaurs, we must consider several dimensions: length, height, weight, and sometimes even other factors like skull size or bite force. Each metric offers a different perspective on what biggest means, and sometimes dinosaurs top the list in one category while ranking differently in another. Let's start with length, often the first aspect that captures imaginations. Visualizing a dinosaur stretched from snout to tail can be awe-inspiring. Some carnivores measured well beyond 10 meters, 33 feet, and even exceeded 13 meters, 43 feet. But simply knowing length doesn't tell the whole story, because body shapes varied dramatically. A slender, agile predator might be almost as long as a more heavily built rival, but obviously differ greatly in mass and strength. Height, usually measured to the top of the hips or the highest point of the animal's body when standing naturally, also provides insight, but it too can be deceptive without context. Theropod dinosaurs, the group that includes most meat-eaters, had varied postures and limb proportions. Some had relatively low-slung bodies built for stealth and speed, while others bore high crests, sail-like spines, or massive heads elevated above their shoulders. Perhaps the most telling, yet also the most challenging metric, is weight. Estimating the body mass of a long-extinct animal requires a fair bit of scientific detective work. paleontologists typically rely on fossilized bones, especially the size and shape of limb bones like femurs and humeri, to infer the amount of muscle and flesh that would have surrounded them. Using these measurements, they apply formulas developed from studies of modern animals to estimate mass. However, because soft tissues rarely fossilize, such estimates involve uncertainty, and different methods can produce a range of values. For example, this is why weight estimates for famous species can vary widely in the scientific literature. One Tyrannosaurus rex individual might be estimated to weigh anywhere between 7 to 14 metric tons, depending on the estimation method and assumptions about body composition. It's also worth keeping in mind that weight alone doesn't always equate to brute strength. The distribution of muscle, bone robustness, and limb mechanics play crucial roles. Skull size itself is another important dimension, especially for carnivores. A massive skull often implies powerful bite force and a predatory lifestyle involving large prey. In comparing dinosaurs such as Allosaurus, Giganotosaurus, and Tyrannosaurus, their skulls rank among the largest of all terrestrial carnivores, sometimes exceeding 1.5 meters, 5 feet in length. The size, shape, and robustness of the skull also provide clues about hunting strategies and feeding mechanisms. Bite force, although something we cannot measure directly from fossils, has been inferred through biomechanical modeling based on muscle attachment sites and bone strength. The bite forces of some giant carnivores rank among the strongest known invertebrates, rivaling or exceeding that of modern crocodiles and great white sharks. Such data helps paleontologists understand which species could crush bones or drive deep puncture wounds, valuable insights into their ecological roles. Yet another interesting metric is the size of individual teeth. Large, serrated teeth were vital tools for carnivorous dinosaurs, helping them slice through flesh and bone. For instance, the shark-toothed Carcharodontosaurids had impressively large teeth, sometimes exceeding 10 centimeters, 4 inches in length. Tooth morphology is a subtle but important factor in assessing overall predatory capabilities. It's also important to emphasize the distinction between the largest species and the largest individual specimens. Species like Spinosaurus, Giganotosaurus, and Tyrannosaurus rex are known for their colossal dimensions, but individual fossils may vary widely within these species due to age, sex, and health. Within a species, the very largest individuals often gain legendary status and provide key reference points in size comparisons. Because much of our measurement depends on incomplete fossils, paleontologists must carefully reconstruct skeletons using the available bones and comparisons to related species. This process, often called scaling or extrapolation, can introduce uncertainties. For example, if a new partial skeleton is discovered missing key parts like the tail or limbs, scientists compare it with better-known relatives to estimate the missing lengths and masses. As new fossils are unearthed, these estimates get revised, and sometimes older records of largest dinosaurs are dethroned. Additionally, some species are known from only fragmentary remains, making confident size estimates difficult and sometimes speculative. It highlights the importance of rigorous scientific methods and caution in publicizing size claims. Paleontologists also use other fascinating metrics such as fossilized footprints or trackways, which can indicate size and walking gait, although these don't provide weight data directly. The length and depth of footprints can help estimate leg length and body mass through biomechanical equations. Such trace fossils offer a dynamic glimpse of dinosaur locomotion and behavior. In recent years, advances in technology have tipped the scales further. Computed tomography, CT scans, and 3D modeling allow researchers to digitally reconstruct skeletons and flesh out muscle anatomy, providing more refined mass estimates and biomechanical insights. These tools have revolutionized how we estimate dinosaur sizes and understand their movements. As a final reflection, measuring the biggest carnivorous dinosaur is more than a numbers game. It's a complex exercise involving piecing together scattered evidence, making informed assumptions, and applying comparative anatomy and modern technology. This multifaceted approach reveals not only the immense scale of these ancient predators, but also the rich tapestry of their lives and adaptations over millions of years. With these concepts in our minds, our journey will continue by tracing the evolutionary path of these predators, from the earliest small hunters to the titanic carnivorous dinosaurs that would later dominate the landscape. Understanding how size develops through evolutionary pressures will enhance our appreciation of these prehistoric marvels. And as we explore those evolutionary stories, the metrics just described will offer the measuring sticks to truly comprehend the giant's true grandeur. As we turn our attention to the sweeping saga of carnivorous dinosaur evolution, we find ourselves tracing an evolutionary journey that is as fascinating as it is complex. A story spanning millions of years, marked by gradual adaptations, environmental pressures, and biological innovations that transformed modest-sized hunters into the colossal apex predators that dominate the fossil record of the Mesozoic era. The origins of carnivorous dinosaurs can be traced back to the late Triassic period, around 230 million years ago, a time when the world was still dominated by the sprawling supercontinent Pangaea. During this epoch, the earliest known theropods, the group that would become the main lineage of meat-eating dinosaurs, were relatively small, bipedal predators, typically less than 2 meters long. These early predators were agile, lightweight hunters, equipped with sharp teeth and claws, designed to seize small prey such as insects, lizards, and early mammals. One of the earliest theropods, Herrerasaurus, found in what is now Argentina, measured roughly 3 to 6 meters in length and combined a slender, graceful build with sharp teeth and claws, reflecting a hunter adapted for speed and nimbleness. These early carnivores occupied an ecological niche that required acute agility and keen senses, hunting in a world shared with other reptiles and primitive dinosaurs. From these humble beginnings, a dynamic evolutionary expansion occurred during the Jurassic period, when climates warmed and ecosystems flourished. This period saw the emergence of larger, more powerful theropods, as niches expanded with an increase in the size and diversity of herbivorous dinosaurs. As prey grew larger, predators were subjected to evolutionary pressure favoring increased body size, more robust bones, and more formidable weaponry. Jurassic carnivores such as Allosaurus and Ceratosaurus embodied this transition. Allosaurus, perhaps the most iconic Jurassic predator, reached lengths up to 9 to 12 meters and developed strong, muscular limbs, robust jaws, and serrated teeth capable of slicing through thick hides. These traits suggest a hunting style involving powerful bites combined with agility, capable of tackling sizable herbivores like stegosaurs and sauropods. This increase in size and diversity paralleled environmental factors, such as abundant, lush vegetation, generating vast herbivore populations, creating ample food resources for large carnivores. Moreover, the breakup of Pangaea started creating geographic isolation, which propelled speciation and contributed to the diversity of theropod lineages evolving independently across continents. Advancing into the Cretaceous period, the trend toward gigantism among carnivorous dinosaurs becomes even more pronounced. This era witnessed the evolution of some of the largest land predators in Earth's history. Among these were the Carcharodontosaurids, a group known for enormous size and shark-like teeth, and Spinosaurids, distinctive for their elongated skulls and semi-aquatic adaptations. Carcharodontosaurus, Giganotosaurus, and Mapusaurus emerged in the southern continents, growing well beyond 12 meters in length and tipping the scales at several tons. These behemoths hunted immense sauropods, their sheer size and powerful bites enabling them to dominate even the largest herbivores. Meanwhile, Spinosaurus, arguably among the most unusual carnivores, adapted to a watery environment, with elongated jaws and conical teeth specialized for catching fish, while still capable of terrestrial predation. Concurrently, the tyrannosaurids evolved in the northern continents, culminating in the arrival of Tyrannosaurus rex in the late Cretaceous. Starting from small two-legged hunters, tyrannosaurids gradually developed larger skulls with bone-crushing teeth, powerful neck muscles, and an overall robust build. Compared to their earlier theropod relatives, T-Rex represented a pinnacle of evolution towards a compact, heavily muscled carnivore with unparalleled bite force. It is important to note that this evolutionary sequence was not simply a linear progression toward larger size. Environmental conditions, competition, and available prey influenced diverse adaptations. Some carnivorous theropods remained relatively small and highly agile, thriving in niches where speed and maneuverability were advantageous. Meanwhile, the largest predators adapted to dominate their ecosystems through sheer power and size. Throughout this evolutionary march, paleontologists observe fascinating shifts not only in size, but also in behaviors and physical traits. The development of keen binocular vision, improved respiratory systems, and even evidence of feathers in some theropods suggest a complex interplay of survival strategies, many of which contribute insights into the lineage that eventually gave rise to modern birds. In tracing the arc from small, swift hunters to the towering giants of the late Cretaceous, we gain a deeper appreciation for how environmental dynamics, ecological pressures, and evolutionary innovation sculpted the carnivorous dinosaurs. They were not mere monstrous beasts, but exquisitely adapted apex predators reflecting the intricate ecosystems of their time. As we begin to meet individual giants, starting with the formidable predators of the Jurassic, such as Allosaurus, we'll see how these evolutionary themes manifest in anatomy, behavior, and the fossil record, bringing to life the diversity and grandeur of carnivorous dinosaurs through Earth's deep history. The tale of early predators, specifically the rise of the theropods, is a key chapter in the story of carnivorous dinosaurs. It is a story that begins deep in the late Triassic, roughly 230 million years ago, when the first recognizable theropod dinosaurs emerged in a world very different from our own. Understanding this rise not only sheds light on where the giants of later periods originated, but also reveals the evolutionary innovations that allowed these animals to become dominant predators across the globe. The earliest theropods were part of the larger dinosaurian radiation that transformed the Triassic ecosystems. Before the dinosaurs claimed their reign, the land was largely dominated by other reptilian groups like the phytosaurs, crocodile-like reptiles, and various archosaurs, the broad group of reptiles that would eventually contain dinosaurs. Dinosaurs initially were just one group among many competitors, but thanks to a suite of evolutionary advantages, theropods in particular carved out a niche as adept meat-eaters. Theropods are characterized primarily by their bipedal stance, walking on two legs, which freed their forelimbs from locomotion and allowed the evolution of sharp, grasping claws and powerful hands used for hunting and manipulating prey. The structure of their hips, skulls, and feet provided a lightweight but powerful frame, ideal for active predation. One of the earliest known theropods, Eoraptor from Argentina, was small, about a meter long, and lived around 231 million years ago. It is considered a basal or primitive theropod, possessing features linking dinosaurs to their non-dinosaurian ancestors. Its lightly built body, sharp teeth, and agility suggest it was an opportunistic carnivore, likely hunting smaller vertebrates and scavenging. Moving slightly forward in time, we find Herrerasaurus, also from the late Triassic, a more advanced and larger predator measuring 4 to 6 meters in length. Herrerasaurus displays a mosaic of features, some similar to later theropods, others unique. Its powerful jaws and sharp, serrated teeth indicate a predatory lifestyle at the top of its food chain. During the early Jurassic, theropods diversified rapidly. This was a time when the climate had stabilized following the turmoil of the Triassic, and ecosystems expanded with increased plant diversity supporting growing herbivore populations. This diversification fostered theropods ranging from small, quick hunters to more sizable predators, such as Dilophosaurus, known from North America, which reached lengths of up to 6 meters and showcased a distinctive pair of crests on its skull. These crests may have served purposes in display or species recognition, reflecting the evolving complexity not only in their physiology, but in their social behaviors. The success of early theropods owes much to several evolutionary traits. First, their heterodont dentition, different types of teeth within the mouth, allowed more sophisticated handling of prey, from slicing flesh to holding on to struggling victims. Second, their advanced sensory capabilities, including forward-facing eyes that provided depth perception, gave them a predatory edge. Additionally, theropods possessed hollow bones and a bird-like respiratory system that improved their metabolism and endurance. These adaptations likely made them agile and effective hunters, capable of sustained chases and tactical strikes. The rise of theropods was not unchallenged, though. They faced competition from other archosaurian predators like Rauisuchians, large, heavily built crocodile-line reptiles. However, as Rauisuchians dwindled and eventually went extinct by the end of the Triassic, theropods took over the dominant predatory niches on land. As the Jurassic progressed, theropods continued to grow both in size and diversity. The middle and late Jurassic record reveals forms like Megalosaurus, one of the first dinosaurs recognized by science, and Allosaurus, which would become one of the apex predators of the time. These dinosaurs displayed more robust bodies, longer legs, stronger jaws, and larger teeth, all indicative of advancing predatory specialization. Theropods also diversified in their ecological roles. Not all were strictly large-bodied carnivores. Some evolved smaller sizes and more specialized diets, while others experimented evolutionarily with different hunting strategies. For example, the comically named Ceratosaurus sported a distinctive nasal horn, which may have played roles in intraspecies signaling or combat. This period laid the evolutionary groundwork for later giants of the Cretaceous, the likes of Giganotosaurus, Spinosaurus, and Tyrannosaurus rex. But it was here, in the Triassic and Jurassic, that the theropods solved many fundamental anatomical and ecological puzzles. They perfected bipedal locomotion, refined their predatory tools, and began occupying varied terrestrial niches. In tandem with their evolution, ecosystems themselves grew more intricate, setting the stage for an intense evolutionary arms race between predators and prey. As herbivorous dinosaurs like the stegosaurs, sauropods, and ornithopods evolved body armor, increased size, and herd behaviors, theropods responded by increasing size, developing stronger assault anatomy, and possibly more complex hunting behaviors. By understanding the rise of the theropods, we grasp the origins of a lineage that would leave an indelible mark on Earth's history. It also helps us see the incremental, yet powerful, forces of evolution shaping dinosaurs over millions of years. This fascinating journey naturally sets us up to explore some of the earliest famous theropod predators in greater detail, starting with the mighty Allosaurus, whose fossils have painted a vivid picture of Jurassic predatory dominance. Our path forward will reveal how these early giants lived, hunted, and ruled their environments with unmatched prowess. Allosaurus stands as one of the most iconic and fascinating carnivorous dinosaurs from the Jurassic period, a true apex predator that roamed the Earth roughly between 155 and 145 million years ago. Its story is not just one of sheer size or ferocity, but also of a creature exquisitely adapted to its environment and ecological role, representing a key stage in the evolution of giant theropod predators. The name Allosaurus means different lizard, a nod to the unique features in its anatomy that distinguished it from earlier, more primitive theropods. Found predominantly in the late Jurassic strata of North America, especially the Morrison Formation, a geological treasure trove that has yielded countless dinosaur fossils, Allosaurus was the dominant carnivore of its time, reigning over vast floodplains, forests, and river systems. In terms of size, Allosaurus was a formidable predator, measuring typically between 8 to 12 meters, 26 to 39 feet in length. Estimates of its weight generally fall around 1 to 2 metric tons, though some individuals might have tipped the scales heavier. Its skull could reach up to 90 centimeters, about 3 feet, long, equipped with dozens of sharp, serrated teeth, perfectly designed for slicing through flesh and bone. One of the most distinctive features of Allosaurus was its skull architecture. Despite its large size, the skull was lightweight and constructed with many openings called fenestrae, which decreased bone weight without compromising strength. A brilliant adaptation for an active predator. The jaws were powerful, and the serrated teeth were continually replaced throughout the dinosaur's life, ensuring it maintained a fearsome arsenal. Its forelimbs were proportionally large and muscular compared to later theropods, such as Tyrannosaurus rex. Allosaurus had 3-fingered hands tipped with sharp claws, which it likely used to grasp and hold on to struggling prey. This contrasts with the small, 2-fingered forelimbs of some later giants, reinforcing the idea that Allosaurus may have relied more on coordinated use of jaws and hands during hunting. The hunting strategy of Allosaurus has been a subject of scientific interest and debate, but several lines of evidence suggest it was an active predator capable of taking down large herbivorous dinosaurs. Fossils of stegosaurs, sauropods, and ornithopods discovered in the same formations show signs of Allosaurus attack, such as bite marks and healed injuries. Paleontologists propose that Allosaurus may have employed a combination of powerful bites and slashing forelimbs to subdue prey. Some biomechanical studies suggest its jaws could open extremely wide, allowing it to deliver deep wounds. There are also hypotheses proposing that Allosaurus may have used a striking method with its neck and head, a sort of hatchet attack, where it sunk its tooth-laden jaws into the victim and then pulled back with force, potentially aided by its robust neck muscles. Social behavior in Allosaurus is an intriguing and ongoing research area. Unlike some other large theropods thought to be solitary, there is evidence suggesting that Allosaurus might have engaged in pack or group hunting. Multiple Allosaurus bone beds have been found where numerous individuals died together, though interpretations vary on whether this reflects social behavior or is a result of environmental accidents. Looking beyond its physical traits and behavior, Allosaurus is fundamental in understanding the ecosystems of the late Jurassic. It occupied the apex of a vast food web, where herbivorous giants like Apatosaurus, Diplodocus, and Stegosaurus thrived. This predator-prey dynamic underscores the balance that sustained Jurassic floodplains and forests, with Allosaurus playing the crucial role of controlling herbivore populations and maintaining ecosystem health. From a broader paleontological standpoint, Allosaurus embodies an evolutionary crossroads. It retains primitive features such as grasping hands, while displaying more advanced traits that presage later theropod super-predators of the Cretaceous. Its fossils have provided rich insights into dinosaur anatomy, growth patterns, and paleobiology. The Morrison Formation, the primary source of Allosaurus fossils, offers remarkable clarity into this giant predator's life. Abundant remains of multiple species found together create an intricate snapshot of the world Allosaurus inhabited. An environment punctuated by rivers, floodplains, and forests with climatic conditions fostering a diverse array of dinosaurs. In summary, Allosaurus was a powerful and versatile predator that dominated its Jurassic world, showcasing impressive adaptations in size, weaponry, and behavior. Its place in the fossil record is not just one of prominence, but also one of evolutionary significance, bridging early theropod forms with the colossal carnivores that followed. As we move forward, the story of Allosaurus sets the stage for understanding the next generation of Jurassic giants, like Torvosaurus, and eventually the massive Carcharodontosaurids and tyrannosaurs of the future. Through the lens of Allosaurus, we glimpse the thrilling dance of predator and prey, survival and adaptation that characterized the Mesozoic era. As we continue our exploration of the giants that ruled the Jurassic landscape, Torvosaurus emerges as a fascinating and formidable figure, often overshadowed by its more famous contemporary, Allosaurus, but no less impressive in terms of size, strength, and predatory prowess. Known as one of the largest carnivorous dinosaurs of the late Jurassic period, Torvosaurus strikes a distinct profile among the giant theropods, embodying raw muscular power and robust anatomy that hint at a unique ecological niche among Jurassic apex predators. Torvosaurus, whose name means savage lizard, was first scientifically described in the 1970s based on fossils discovered in North America, particularly the Morrison Formation, the same rich fossil deposit that has provided so many insights into late Jurassic ecosystems. Subsequent discoveries in Europe, including Portugal, have also shed light on its broader geographic range, underscoring Torvosaurus's wide distribution across what was then a connected landmass. In size, Torvosaurus impresses with estimated lengths ranging from 9 to 11 meters, approximately 30 to 36 feet, placing it among the largest known Jurassic theropods. Estimated weights vary, with some individuals tipping the scales close to 2 metric tons or more, making this a predator of considerable physical presence. Yet, unlike the relatively gracile build of Allosaurus, Torvosaurus possessed an exceptionally robust and heavily muscled form. Its massive forelimbs, bearing powerful claws, and heavily built skull with large teeth adapted for bone-crushing bites suggest a predator tailored for strength, rather than speed. One of the defining characteristics of Torvosaurus is its remarkable arm strength. Its forelimbs were proportionally larger and more muscular than those of many of its carnivorous peers. The claws alone could reach impressive sizes, and were likely used for grappling with prey or tearing into carcasses. In the competitive environments of the late Jurassic, such anatomical adaptations might have offered an advantage in overpowering prey or competing with other predators. The skull of Torvosaurus was broad and reinforced with robust bones, topped with a set of serrated teeth designed for slicing through flesh and possibly crushing bone. This combination of features emphasizes its role as an apex predator that could handle the large sauropods and heavily armored stegosaurs that populated its habitat. While Allosaurus is hypothesized to have used a slashing hatchet bite, Torvosaurus's bone-crippling jaws may have served more of a destructive, overpowering function. Interestingly, recent studies suggest that Torvosaurus was more heavily built and less adapted for fast running than some other Jurassic carnivores. This likely means it employed a hunting strategy that relied on ambush or short bursts of power, rather than prolonged high-speed chases. The Morrison Formation, with its complex mosaic of rivers, floodplains, and forests, provided the perfect stage for such a tactic, with plenty of cover and large herbivorous dinosaurs to hunt. While the fossil record for Torvosaurus is more limited compared to Allosaurus, finds of partial skeletons, teeth, and footprints have been invaluable in constructing a clear picture of its biology and lifestyle. Importantly, these fossils demonstrate that Torvosaurus coexisted sympatrically with other large theropods, hinting at a complex predator guild where different species avoided direct competition by occupying distinct niches, a process known as niche partitioning. The late Jurassic ecosystems were rich and diverse, hosting a plethora of gigantic sauropods like Apatosaurus, Diplodocus, and Brachiosaurus, alongside armored stegosaurs such as Stegosaurus. Torvosaurus's robust design appears well-suited to hunting these massive herbivores or scavenging their carcasses. Evidence of bite marks on fossil bones attributed to Torvosaurus supports this predatory behavior. Beyond its anatomy and ecological role, Torvosaurus also provides fascinating cultural and scientific significance. As one of the relatively less publicized giants of the Jurassic, it offers a compelling example of how predator diversity was broader and more complex than once assumed, challenging earlier notions that a single dominant carnivore monopolized these ecosystems. Moreover, discoveries of Torvosaurus fossils in both North America and Europe elucidate important paleogeographic connections during the Jurassic, indicating faunal exchanges across continents before the full breakup of Pangaea in subsequent periods. These finds help paleontologists understand evolutionary patterns, dispersal routes, and environmental variations influencing dinosaur distribution. In summary, Torvosaurus stands as a muscle-bound giant of the late Jurassic, a symbol of raw power and predatory specialization. Its evolutionary story complements and contrasts with its better-known contemporaries, highlighting the rich tapestry of dinosaur diversity and adaptation. As we segue into the next chapters of our journey, exploring the Carcharodontosaurids of Africa and their own claims to the title of giant meat-eaters, Torvosaurus serves as a powerful reminder that the age of dinosaurs was not defined by a single ruler, but by a varied ensemble of predators, each uniquely adapted to their time and place. As we journey from the heavily muscled Torvosaurus of the late Jurassic into the towering realms of the early and mid-Cretaceous, our path takes us to Africa, where an extraordinary group of giant carnivorous dinosaurs, the Carcharodontosaurids, rose to dominance. These monstrous meat-eaters carved their niche as some of the largest terrestrial predators that ever lived, showcasing evolutionary adaptations that distinguished them from their Jurassic predecessors and cemented their reputation as apex hunters of their time. The Carcharodontosaurids, named after their distinctive shark-like teeth, carcharodon meaning shark tooth, belong to a group of large theropod dinosaurs characterized by massive, serrated teeth, formidable skulls, and a robust yet somewhat streamlined body plan tailored for overpowering large prey. These giants primarily flourished during the early to mid-Cretaceous period, roughly between 130 and 90 million years ago, and their fossils have been unearthed on several continents, though Africa offers some of the richest records. The African Carcharodontosaurids thrived in diverse environments that ranged from semi-arid plains to lush coastal regions. Their fossil discoveries, notably in nations like Morocco, Niger, and Egypt, have provided a window into ecosystems pulsating with life, where these predators occupied the apex niche left by the shrinking dominance of earlier theropods like Spinosaurids and Abelisaurids. Among the most famous representatives of this family is Carcharodontosaurus, whose size rivaled or perhaps even exceeded that of the contemporaneous giant tyrannosaurs of North America. Estimates suggest that some African Carcharodontosaurids reached lengths of up to 13 meters, over 40 feet, and weighed between 6 and 8 metric tons. staggering dimensions that underline their top-tier predatory status. What truly sets Carcharodontosaurids apart is their impressive cranial anatomy. Their skulls were long and narrow but highly robust, built to resist the stresses encountered during violent biting and twisting motions as they dismembered massive prey. The shark-like, blade-shaped teeth could grow up to 15 centimeters, 6 inches, in length, serrated for maximum slicing efficiency. Perfect for inflicting deep wounds on large sauropods and other herbivores. The morphology of the Carcharodontosaurid body reflects a balanced blend of power and agility. Unlike some bulkier theropods with thick-set builds, these predators maintained relatively long legs, which likely afforded them decent speed for animals of their enormous size. Such an adaptation would have been essential for ambushing or chasing down prey on the vast African floodplains and woodlands. The ecological impact of African Carcharodontosaurids was enormous. In the richly diverse Cretaceous ecosystems, these apex predators contended with a variety of enormous herbivorous dinosaurs, from massive titanosaurs spanning several tens of meters to hadrosaurs and other ornithopods. Their hunting strategies presumably leveraged their formidable bite force, combined with precision slashing bites, relying on physical power rather than endurance pursuit. Fossil evidence suggests these dinosaurs were solitary hunters, but may have exhibited complex behaviors, including territoriality and possibly parental care, though this remains an area of active research and debate. Their presence arguably influenced the behavior and evolution of contemporaneous herbivores, driving defensive adaptations such as body armor, herd dynamics, and migration patterns. Notably, the discovery of Carcharodontosaurid fossils in northern Africa in the early 20th century, such as the famous Carcharodontosaurus saharicus, initially challenged prevailing ideas about the distribution and diversity of mighty carnivores. It revealed that giant predators were not confined to the familiar dinosaur-rich deposits of North America or Eurasia, but flourished globally in exceptional diversity. Beyond Carcharodontosaurus, the Carcharodontosaurid family includes other notable genera from Africa, like Suchomimus, which also displays a fascinating combination of features, including a long, crocodile-like snout, hinting at semi-aquatic or varied feeding habits. Some relatives exhibit evolutionary experimentation in skull and limb anatomy, underscoring the adaptability and diversity of this group. In sum, the Carcharodontosaurids of Africa were titans of their time, creatures of immense strength, terrifying dentition, and ecological influence. Their reign over the Cretaceous landscapes embodied the relentless drive of evolution toward size, specialization, and power. They were more than mere monsters. They were finely honed predators, products of a complex interplay between environment, prey abundance, and evolutionary opportunity. As we move forward to examine particular species like the enigmatic Carcharodontosaurus and the South American giants such as Giganotosaurus, we will uncover the varied faces of these Carcharodontosaurids, each a marvel of evolutionary engineering and a testament to the diverse tapestry of prehistoric life. Carcharodontosaurus, whose name fittingly means shark-toothed lizard, stands as one of the most awe-inspiring theropods in Earth's prehistoric history. This colossal predator roamed the mid-Cretaceous landscapes approximately 100 to 93 million years ago, primarily across what is now North Africa. As a member of the Carcharodontosaurid family, Carcharodontosaurus represents the apex of evolution among its fierce kin, distinguished by its immense size, distinctive dentition, and formidable predatory adaptations. Visualizing Carcharodontosaurus, it is nearly impossible to overlook its sheer scale. Estimates suggest this dinosaur stretched between 12 to 13.3 meters, 40 to 43 feet in length, with some exceptional specimens potentially reaching even longer sizes. It likely weighed between 6 and 15 metric tons, positioning it as one of the largest terrestrial carnivores to ever exist, rivaling or even surpassing the famed Tyrannosaurus rex in mass and length. The skull of Carcharodontosaurus is a masterpiece of evolutionary engineering. Measuring roughly 1.6 meters, over 5 feet long, it was characterized by a broad yet lightly built structure filled with an array of serrated, blade-like teeth, similar in design to those of modern sharks, hence the name shark-toothed. These teeth could grow up to 15 centimeters, 6 inches, or more in length, exquisitely adapted for slicing through the flesh of large prey and delivering devastating wounds. Its cranial anatomy reveals fascinating details. The jaws, while powerful, were not built for bone crushing in the same way as tyrannosaurids. Instead, Carcharodontosaurus employed wide, horizontal, scissor-like bite motions designed to shear through muscle and tendon efficiently. This indicates a different hunting strategy, favoring precise slashes over the crushing power approach. Evidence from bite marks and fossilized wounds suggests that it hunted enormous sauropods and other large herbivorous dinosaurs, making effective use of its large-sized teeth and formidable biting technique. Carcharodontosaurus's body reflected a balance between strength and agility. While massive, it possessed relatively long legs compared to some other large theropods, which likely allowed it more mobility and the ability to execute bursts of speed when hunting. Its long tail would have served as a counterbalance to its heavy head, aiding in stability and maneuverability during pursuit or combat. An intriguing feature of Carcharodontosaurus is the presence of crests above its eyes, somewhat reminiscent of those found on Allosaurus. These bony ridges might have played roles in display behaviors, species identification, or intra-species combat. Such ornamentation adds to the complexity of its biology, suggesting a dinosaur that was not only a fearsome predator, but also socially and behaviorally nuanced. From the ecological perspective, Carcharodontosaurus occupied the top tier in African Cretaceous food webs. Its prey included giant titanosaurian sauropods, which were among the largest animals to ever walk the earth. Hunting or scavenging such behemoths required immense power, but also tactical cunning. Carcharodontosaurus's adaptations offered a combination of brute force and precision, making it a highly effective carnivore. Fossil discoveries of Carcharodontosaurus reached public attention, with spectacular specimens excavated in Egypt and Morocco during the 20th century, gradually revealing the grandeur of this predator. Some partial skeletons have been crucial in reconstructing its skeletal layout, confirming its size and anatomical peculiarities. These fossil finds also sparked debates. For decades, the distinction between Carcharodontosaurus and closely related species was refined through comparative analysis of skull shape, teeth, and vertebrae. The Eurasian theropod Neovenator and South American Giganotosaurus share many traits with Carcharodontosaurus, attesting to a fascinating evolutionary lineage of giant carnivores spread across continents during the mid-Cretaceous. Modern scientific techniques, including CT scanning and biomechanical modeling, have furthered our understanding of Carcharodontosaurus. Studies shed light on its likely muscle structure, bite force, and possible hunting behaviors, deepening the picture of a dynamic, fearsome predator perfectly adapted to dominate its ecosystem. In summary, Carcharodontosaurus stands as a hallmark of carnivorous dinosaur evolution, a shark-toothed titan built for power and precision. It embodies the relentless drive of natural selection towards gigantism and specialization, an apex predator in a complex and vibrant Cretaceous world. As we continue to explore giant carnivorous dinosaurs, we will soon delve into Giganotosaurus of South America, a predator that shared a close kinship and mystery comparable to that of Carcharodontosaurus, unveiling another chapter in the epic story of these prehistoric titans. Giganotosaurus carolini, often hailed as Argentina's hunter king, is one of the most extraordinary carnivorous dinosaurs to have walked the earth, representing not merely a colossal predator, but a key piece in understanding the grandeur and diversity of southern hemisphere theropods. Lived during the late Cretaceous, approximately 98 to 97 million years ago, this gigantic predator dominated the ecosystems of present-day South America, showcasing an impressive blend of size, power, and evolutionary adaptation. Discovered in 1993 in the Patagonia region of Argentina, Giganotosaurus immediately captured the imagination of paleontologists and the public alike due to its vast size. Initial estimates detected that it rivaled, if not exceeded, the famed North American Tyrannosaurus rex in length, measuring roughly between 12 and 13.5 meters, about 39 to 44 feet. Its robust model suggests a weight of approximately 8 to 13 metric tons, firmly placing it among the largest terrestrial carnivores ever to have existed. The name Giganotosaurus fittingly means giant southern lizard, reflecting both its gargantuan body and its geographic placement. It belongs to the Carcharodontosauridae family, a group of massive shark-toothed carnivores known for their immense skulls and powerful jaws. Examining the skull of Giganotosaurus reveals a formidable tool designed for efficient predation. The skull extended about 1.5 meters, nearly 5 feet, bearing razor-sharp teeth with finely serrated edges optimized for cutting flesh. Unlike the bone-crushing bite of the T-Rex, Giganotosaurus's jaws seem adapted more for slicing, suggesting a predatory style focused on immobilizing and deboning large prey through swift, destructive bites rather than pulverizing bone. Limb proportions provide further insight into its predatory capabilities. Though massive, its hind limbs end in powerful three-toed feet that allowed for surprising bursts of speed, crucial when hunting enormous herbivorous titanosaurs like Argentinosaurus, some of the largest animals ever to have lived. The forelimbs, however, were comparatively small but armed with sharp claws, likely used to grasp struggling prey or manipulate carcasses. Giganotosaurus inhabited the vast floodplains and forested regions of Patagonia, a landscape teeming with gigantean sauropods, as well as smaller ornithopods and theropods. Its coexistence with prey, like the huge Argentinosaurus, reinforces the image of a giant predator capable of hunting prey several times its own size. Scientists theorize that, in tackling such massive herbivores, it employed coordinated hunting techniques or strategic ambush tactics, though precise behaviors remain speculative. Intriguingly, recent discoveries close to the original find site revealed remains of multiple individuals in surprisingly close proximity. This has led some paleontologists to hypothesize that Giganotosaurus may have exhibited social or pack behavior, a notion quite extraordinary for such massive theropods, potentially enabling them to tackle even the largest prey collaboratively. Comparisons with its close relative Carcharodontosaurus, whose fossils have been found across Africa and possibly Europe, shed light on the distribution and divergence of carcharodontosaurids across continents during the mid-Cretaceous. Their shared characteristics highlight evolutionary parallels, yet geographic separation facilitated distinct adaptations to their respective environments. Studying Giganotosaurus has profoundly influenced the field of paleontology, challenging prior assumptions that Tyrannosaurus rex was the largest land predator. Instead, Giganotosaurus, along with other giants like Carcharodontosaurus and Spinosaurus, underscores the diversity of superpredators that evolved in different parts of the world. The discovery and analysis of Giganotosaurus continue to enrich our understanding of predator-prey dynamics and ecosystem structure in the Cretaceous, illustrating the evolutionary pressures that molded such massive carnivores. It's a symbol of prehistoric might and an exemplar of how Earth's shifting continents and climates fostered remarkable biological experiments in size and predation. In the upcoming segment, we will explore Mapusaurus, another giant from Argentina, which adds further richness to the discussion of giant carnivorous dinosaurs and prompts fascinating questions about possible pack hunting behaviors among these titans. The story of Giganotosaurus thus forms not just a testament to individual grandeur, but a stepping stone toward understanding the complex social and ecological realities of the largest predators in history. Moving forward from the monumental presence of Giganotosaurus, we encounter Mapusaurus roziae, another titan among the giant carnivorous dinosaurs of the late Cretaceous, whose fossil record has ignited one of the most intriguing debates in paleoecology: the possibility that these colossal predators may have hunted in packs. Mapusaurus first came to scientific attention through a remarkable discovery in Argentina's Patagonia, within sedimentary layers dated to approximately 97 million years ago. This predator offers a unique window into the social behaviors and hunting strategies that may have governed the lives of some of the largest terrestrial meat-eaters in history. Like its close relative Giganotosaurus, Mapusaurus was a member of the Carcharodontosaurid family, sharing many anatomical features typical of this group: massive size, powerful jaws lined with sharp, serrated teeth, and a flexible yet sturdy body built for strength and speed. Estimates place Mapusaurus at lengths ranging from 10 to 12 meters, about 33 to 39 feet, with weights approaching 5 to 7 metric tons. While not necessarily the largest theropod ever known, Mapusaurus was nevertheless an apex predator, a land-dwelling giant built to dominate its ecosystem. What truly distinguishes Mapusaurus in the annals of dinosaur paleontology is the unique context in which its fossils were found. Unlike many solitary remains of other giant predators, paleontologists uncovered a bone bed containing the disarticulated but clearly contemporaneous remains of multiple individuals of different ages and sizes. This assemblage includes juveniles, subadults, and fully grown adults, all located within a relatively concentrated area. Such a discovery is unusual and suggests the possibility of group behavior. From this, scientists have posited that Mapusaurus might have hunted in packs, or at least lived in groups, a theory supported by modern analogs in the animal kingdom, where social hunting imparts significant advantages, especially when tackling prey larger or more dangerous than oneself. Given the overwhelming size of the herbivores these predators faced, enormous titanosaurs that dwarfed even the largest carnivores, coordinated hunting strategies could have been essential to bring down such leviathans. While behaviors of extinct animals can never be observed directly, the notion of pack hunting among giant theropods like Mapusaurus is supported by both the fossil evidence and biomechanical considerations. Tackling a sauropod several times larger in weight would have demanded cooperation, coordinating roles, and complex communication, traits linked to sociality and intelligence in living predators. Additional anatomical features of Mapusaurus may lend indirect support to social behavior. For instance, its relatively agile limbs, large forward-facing eyes providing enhanced binocular vision, and a lighter skull compared to other giant predators suggest adaptations consistent with active pursuit and coordinated hunting tactics rather than solitary ambush. Skeptics caution that the fossil bone bed could represent a mass mortality event, perhaps caused by a flood or drought, lodging several dinosaurs in the same place without implying social behavior. However, the growing volume of comparative evidence from related species highlights the increasing acceptance within the scientific community that at least some large theropods may have been social animals. If Mapusaurus truly engaged in pack hunting, this behavior would parallel that of some modern apex predators such as wolves and lions, emphasizing that complex social strategies to increase hunting success have deep evolutionary roots. Such sociality could also have had implications for offspring survival, territory defense, and resource sharing within the group. From a paleoecological perspective, pack hunting by giant theropods like Maposaurus would have shaped the structure of late Cretaceous ecosystems profoundly. The pressure exerted on giant herbivores could influence migration patterns, herd behaviors, and reproductive strategies, contributing to a dynamic and balanced environment. In the broader context of carnivorous dinosaur evolution, Maposaurus demonstrates how these prehistoric giants were not mere solitary beasts, but potentially complex animals capable of social interaction and collaboration. This insight enriches our perception of these titans and opens stimulating avenues for further research into dinosaur behavior. As we continue our exploration, we will next turn to another enigmatic giant, whose lifestyle and size continue to fascinate scientists: Spinosaurus. Its semi-aquatic habits and debated dimensions add a captivating twist to the tale of the biggest carnivorous dinosaurs in history, further expanding our understanding of the diverse adaptations that allowed these predators to thrive across varied environments. Spinosaurus aegyptiacus stands among the most enigmatic and captivating carnivorous dinosaurs ever discovered. Its story is a tale blended with mystery, debate, and groundbreaking scientific revelations. This river monster of the Cretaceous emerged as a unique and formidable predator, challenging many traditional notions of what a giant land-based carnivore could be. Its size, aquatic adaptations, and ecology have incited vibrant debates among paleontologists, shaping our understanding not only of Spinosaurus itself, but also of the broader diversity of prehistoric life. Spinosaurus lived during the mid-Cretaceous period, approximately 112 to 93 million years ago, primarily in what is now North Africa, regions that were once vast river systems and lush deltas. The first fossil remains were unearthed in Egypt in the early 20th century, but much of the original material was lost during World War II, contributing to the long-standing uncertainties surrounding this dinosaur's anatomy and size. Traditionally, Spinosaurus was reconstructed as a large bipedal predator resembling other giant theropods, but with a distinctive sail-like structure formed by elongated neural spines projecting from its vertebrae. Early estimates of its size placed it among the largest carnivores, rivaling or even exceeding Tyrannosaurus rex and Giganotosaurus, with estimates of length ranging widely from 12 to over 17 meters, 40 to 56 feet. In recent decades, however, new fossil discoveries and advanced technologies have revolutionized our understanding of Spinosaurus, revealing that it was not just another giant land predator, but instead uniquely adapted for a semi-aquatic lifestyle. Several anatomical traits highlight its aquatic specialization. These include a long, narrow, crocodile-like skull filled with conical teeth suited for catching slippery prey such as fish, stout and paddle-like limbs that suggest swimming prowess, dense limb bones to aid buoyancy control, and a tail with a broad, fin-like shape capable of powerful side-to-side propulsion, akin to modern aquatic animals. This distinct morphology implies that Spinosaurus spent a significant portion of its life in water, hunting aquatic creatures in rivers and coastal environments rather than pursuing land-based dinosaurs. Such a niche partitioned Spinosaurus from terrestrial predators and opens a window into a more diverse and ecologically complex Cretaceous world. The debate over Spinosaurus's size is ongoing and nuanced. Some well-preserved specimens have confirmed lengths exceeding traditional giant theropods, with one remarkable fossil suggesting a total length of up to 15 to 16 meters, 50 feet, though precise mass estimates vary due to its unique body proportions, more elongated and less bulky than tyrannosaurs or carcharodontosaurids. The lower body mass relative to length reflects adaptations for an aquatic environment, including lighter bones and a less robust pelvic region. These findings challenge assumptions linking size exclusively with land-dwelling bulk and reinforce the idea that Spinosaurus is a paradigm-shifting dinosaur bridging the worlds of land and water. Yet, Spinosaurus has sparked controversies and debates beyond size and lifestyle. Disagreements focus on its posture and locomotion, how well it could walk on land, whether it was truly quadrupedal, as some studies propose, and what role its enormous back sail played. Hypotheses range from the sail being a display structure for thermoregulation or mating, to it functioning as a swimming aid or fat storage area. Fascinatingly, the aquatic adaptations of Spinosaurus also raise questions about convergent evolution, where unrelated species evolve similar traits to adapt to comparable environments. Its crocodilian-like skull and swimming tail are prime examples of evolutionary convergence with modern aquatic reptiles, underscoring nature's inventive solutions to shared ecological challenges. In terms of behavior, Spinosaurus likely preyed on large fish, crocodilians, and perhaps small to medium-sized dinosaurs near shorelines. Its discovery has widened perspectives on niche diversity among the largest theropods and hints at ecosystems that supported diverse predator guilds with specialized food habits. In sum, Spinosaurus stands as a titanic testament to evolutionary flexibility. Far from a simple giant terrestrial beast, it is a revolutionary figure reshaping how we think about dinosaur ecology, diversity, and adaptation. As we continue to unravel the stories of the prehistoric giants, our next focus will be on Acrocanthosaurus, a high-spined predator from North America, whose distinct anatomy offers another fascinating glimpse into the varied forms of carnivorous dinosaurs. The saga of Spinosaurus reminds us that the age of dinosaurs was rich not just in size, but in ecological innovation and mystery. Acrocanthosaurus atokensis, often referred to as the high-spined lizard, occupies a fascinating place in the annals of North American paleontology as one of the largest and most distinctive carnivorous dinosaurs of the early Cretaceous period. Living approximately 115 to 105 million years ago, this predator's unique anatomy, marked notably by its elongated neural spines along the back, sets it apart from many other theropods, offering intriguing insights into the diversity and specialization of prehistoric apex hunters. The fossils of Acrocanthosaurus primarily hail from the south-central United States, states such as Oklahoma, Texas, and perhaps Arkansas, revealing a creature that dominated expansive floodplains, river valleys, and subtropical landscapes characterized by diverse flora and fauna. Though the fossil record of Acrocanthosaurus is not as abundant as some other theropods, the specimens discovered have provided critical information about its physical build, behavior, and ecological role. In terms of size, Acrocanthosaurus was a giant, measuring between 11 and 12 meters, 36 to 39 feet in length, with estimated weights reaching up to 6 to 7 metric tons. These dimensions place it among the largest predators of its time, comparable in size with some later Cretaceous carnivores, although it predates the arrival of tyrannosaurids in North America by millions of years. One of the most striking anatomical features of Acrocanthosaurus is its unusually tall neural spines, elongated bony projections rising from many of the vertebrae along its back and tail. This distinctive, high-spined morphology likely supported a prominent sail or ridge made of flesh, muscle, and possibly skin. While the precise function of this structure remains debated, hypotheses range from thermoregulation, helping the animal dissipate heat or absorb sunlight, to visual display for attracting mates or intimidating rivals. The sail may have also contributed to muscle attachment, enhancing strength and flexibility. The skull of Acrocanthosaurus was large and robust. equipped with long, sharp teeth designed for gripping and tearing flesh. Its jaws were powerful, although not as heavily built as those of later tyrannosaurids. Equipped with three-fingered hands tipped with large claws, it likely used a combination of its jaws and forelimbs to capture and subdue prey. Acrocanthosaurus was an apex predator in an ecosystem rich with large herbivores, including early ceratopsians, ornithopods, and sauropods. Its prey likely ranged from smaller, more agile animals to much larger dinosaurs. Evidence from related species and biomechanical modeling suggests that it had the strength, agility, and sensory capabilities needed to hunt effectively, perhaps relying on ambush tactics or bursts of speed to overcome prey. Interestingly, Acrocanthosaurus belongs to the family Carcharodontosauridae, linking it phylogenetically to massive South American and African giants like Giganotosaurus and Carcharodontosaurus. This connection sheds light on the dispersal and evolutionary history of large predatory dinosaurs during the Cretaceous, suggesting widespread distribution and ecological success. The discovery of Acrocanthosaurus has also held cultural significance, serving as a window into North America's prehistoric past and often featured in museums, documentaries, and literature. Its unique sail and massive frame have captivated public imagination, inspiring artists and scientists alike. Although debates around the exact function of its high spines continue, Acrocanthosaurus remains a testament to the varied strategies carnivorous dinosaurs employed in growing to massive sizes and dominating their environments. Its story enriches our understanding of how ecosystems evolved during the early Cretaceous and the diverse adaptations that underpinned dinosaur success. As we proceed, the journey will lead us toward the tyrannosaurids, the so-called tyrant kings, whose rise in the late Cretaceous would finally eclipse earlier giants and reshape the face of carnivorous dinosaur evolution. But before that, Acrocanthosaurus reminds us of a remarkable lineage of predators that ruled long before the tyrannosaurs cemented their legendary status. The story of the Tyrannosauridae family, the so-called tyrant kings, is one of the most fascinating chapters in the history of carnivorous dinosaurs. These fearsome predators dominated terrestrial ecosystems during the late Cretaceous period, particularly across what is now North America and parts of Asia, and their evolutionary rise marks a remarkable transformation in the world of giant theropods. Understanding the tyrannosaurids' ascent provides insight into how they evolved from modest-sized hunters into the colossal icons so deeply embedded in both science and popular culture. Tyrannosaurids belong to the broader group of theropod dinosaurs, but distinguish themselves with a unique combination of features that set them apart from earlier carnivores, like Allosaurus and Carcharodontosaurids. They first appeared approximately 80 million years ago during the mid to late Campanian stage of the late Cretaceous, and quickly diversified and expanded over the next 15 million years. While initially smaller and more gracile, over time, this lineage evolved larger, more robust forms, culminating with legendary species such as Tyrannosaurus rex. The early tyrannosaurids, such as Apalachiosaurus and Alioramus, were smaller predators that displayed adaptations suited for active hunting, including strong jaws and sharp serrated teeth. But unlike earlier giant predators, which often possessed long forelimbs with 3 functional fingers, tyrannosaurids show a trend toward reduced forelimb size with just 2 fingers. This morphological shift sparked considerable debate about the role these limbs played, with current hypotheses favoring the forelimbs as specialized tools for grasping prey or stabilizing during feeding, rather than primary weapons. One of the most defining features of tyrannosaurids is their massive skulls, which became deeper and more reinforced over time. These enormous skulls housed some of the most powerful bite mechanisms of any land animal to have ever lived. Bite force estimates for large tyrannosaurids, especially T-Rex, range up to 35,000 to 57,000 newtons, enough to crush bone with incredible efficiency. This evolutionary innovation gave tyrannosaurids a significant advantage as apex predators, capable of dispatching prey with devastating bites. Their enhanced sensory systems, impressive binocular vision, acute olfactory capabilities, and large brain cases relative to body size suggest tyrannosaurids were sophisticated hunters with complex behavioral repertoires. These traits allowed them to excel as both stealthy stalkers and powerful ambush predators within their ecosystems. The late Cretaceous witnessed a blossoming of tyrannosaurid diversity, with a range of species occupying different niches, from the massive T-Rex roaming the floodplains of western North America to the somewhat smaller, yet no less agile Tarbosaurus bataar in Asia. Tyrannosaurids dominated diverse habitats and prey landscapes. Their anatomical adaptations enabled them to thrive alongside a variety of ornithischian dinosaurs, hadrosaurs, ceratopsians, and ankylosaurs, forming intricate predator-prey dynamics. The rise of tyrannosaurids coincided with profound changes in Earth's flora and fauna. The decline of earlier, large-bodied theropod groups opened ecological spaces that tyrannosaurids exploited. Additionally, continental configurations and climatic shifts in the late Cretaceous fostered the isolation and differentiation that drove speciation within this family. From a paleontological perspective, the tyrannosaurid lineage showcases an extraordinary example of evolutionary escalation. A relentless drive toward increased size, bite power, and sensory refinement. Their fossils, often remarkably complete, offer vivid snapshots of their biology, growth patterns, and even behavior. Specimens like Sioux, the famed T-Rex from South Dakota, have illuminated growth rates and life histories, contributing to a revolutionary understanding of dinosaur ontogeny. Furthermore, the tyrannosaurid's impact extends far beyond academia into global popular imagination. Their depiction in media, literature, and film has cemented them as symbols of prehistoric power and intrigue, shaping how generations perceive the prehistoric world. As we trace the impressive legacy of the tyrant kings, our next chapter explores Tyrannosaurus rex itself, the most renowned member of this family and perhaps the most famous dinosaur of all time. We will delve into the science behind measuring this legend, dissecting what makes T-Rex an unparalleled giant among giants, and a creature whose mythos extends far beyond the fossil record. Tyrannosaurus rex, often simply called T-Rex, is arguably the most famous dinosaur ever discovered, a towering icon of prehistoric life whose legend has captivated imaginations worldwide. But beyond the popular image lies a complex scientific quest to accurately measure this monster, to understand its true size, weight, and physical prowess, and to place it within the broader context of the largest carnivorous dinosaurs in history. Measuring the legend of T-Rex means combining meticulous fossil analysis, state-of-the-art technology, and an evolving understanding of dinosaur biology. Tyrannosaurus rex lived during the late Cretaceous period, around 68 to 66 million years ago, primarily in what is now western North America. It was one of the last non-avian dinosaurs before the mass extinction event that ended the Mesozoic era. Fossils of T-Rex are remarkably well preserved and abundant compared to many other giant carnivores, providing a rich foundation for scientific study. Determining the size of T-Rex involves estimating both length and weight, metrics that offer different pictures of its formidable presence. The length of T-Rex from snout to tail has been rigorously reconstructed through complete or nearly complete skeletons. Most adult specimens measure about 12 meters, 40 feet in length, though some individuals may have reached lengths up to 13.2 meters, 43 feet. This length alone places T-Rex firmly in the upper echelons of known carnivorous dinosaurs, rivaling or exceeding contemporaries like Giganotosaurus and Spinosaurus in linear dimension. Weight estimation is more complex due to the incomplete nature of soft tissue preservation and the necessity of indirect modeling. Paleontologists use methods such as volumetric reconstructions, where 3D models of the skeleton are created with estimated musculature and soft tissue volumes, plus scaling relationships based on measurements of fossilized bones like femurs and humeri. These analyses suggest that large adult T-Rex individuals weighed between 8 and 14 metric tons, with some exceptionally massive specimens potentially reaching closer to 15 tons. One particularly notable specimen, Scotty, discovered in Saskatchewan, Canada, is currently regarded as the largest known T-Rex individual. Scotty measures approximately 13 meters, 43 feet in length, and is estimated to have weighed around 8.8 metric tons or more, illustrating the upper size limits of the species. Another famous specimen, Sue, housed at Chicago's Field Museum, is slightly smaller but offers the most complete and studied skeleton, helping set standards for T-Rex size and anatomy. Besides overall size, detailed measurement of skull dimensions provides crucial insight into the dinosaur's predatory capabilities. The skull of an adult T-Rex can reach lengths of up to 1.5 meters, over 5 feet, bearing robust teeth over 30 centimeters in length, the largest of any terrestrial carnivore. These teeth were thick, banana-shaped, and serrated, perfectly designed to crush bone and tear through flesh. Bite force is another parameter tightly linked to size and predatory power. Biomechanical modeling, incorporating muscle attachment sites and jaw leverage, estimates T-Rex's bite force to be among the highest recorded for any land animal, with figures ranging up to 57,000 newtons or more, equivalent to over 6 tons of force, enough to crush large bones and break apart carcasses with ease. However, size alone does not fully capture the essence of T-Rex. Age and growth patterns have been studied through bone histology, revealing that T-Rex experienced a rapid growth spurt during adolescence, achieving most of its bulk between ages 14 and 18, before reaching full maturity around 20 years old. This fast growth rate hints at high metabolic demands and dynamic lifestyles. Measurement efforts also extend to understanding locomotion and posture. Studies using biomechanical simulation suggest T-Rex could reach speeds up to 20 to 27 kilometers per hour, 17 miles per hour, balancing its immense size with agility significant enough for an effective predator. Its massive legs, powerful tail, and musculature all contribute to this capacity. In sum, the measuring of Tyrannosaurus rex transcends mere numbers. It is a deep dive into anatomy, physiology, behavior, and ecology. Each data point, be it length, weight, skull size, or bite force, adds layers to the portrait of a creature that was an extraordinarily adapted predator, carving an evolutionary niche dominated by power and precision. As we transition to examine some of the largest known specimens of T-Rex, including Scotty, Sue, and others, we delve even deeper into the magnitude of these individual dinosaurs, enhancing our appreciation for the sheer scale and diversity within this legendary species. Among the many remarkable Tyrannosaurus rex specimens unearthed over the years, a small number stand out for their immense size, completeness, and scientific significance. These giants not only provide invaluable data on the biology and behavior of T-Rex, but also inspire awe as the largest land carnivores known to science. Two of the most famous and well-studied specimens are affectionately known as Scotty and Sue. though there are other remarkable finds that collectively flesh out our understanding of these towering predators. Sioux first burst into public consciousness after its discovery in 1990 near Faith, South Dakota. The fossilized skeleton, an astonishing 90% complete, ranks among the most complete T-Rex specimens ever recovered. Housed now at the Field Museum of Natural History in Chicago, Sioux measures approximately 12.3 meters, 40 feet, in length, and is estimated to have weighed around 8.4 metric tons. The quality and completeness of the fossil have enabled scientists to study the anatomy of T-Rex in unprecedented detail, from bone structure to pathological signs, revealing injuries and infections that offer glimpses into its life struggles. Beyond Sioux's sheer size and completeness, its remarkable preservation has allowed detailed histological studies, including growth ring analysis in bones, confirming that this individual was approximately 28 years old at the time of death. Despite its age, Sioux was a powerful predator, with signs of healed injuries indicating survival through violent encounters, further illuminating the resilience and vigor of T-Rex. Scotty, discovered in Saskatchewan, Canada, in 1991, but only fully excavated and described decades later, currently holds the title of the largest and heaviest T-Rex specimen. Scotty's completeness rivals Sioux's, with over 65% of its skeleton recovered. Measuring an estimated 13 meters, 43 feet, in length, and weighing potentially over 8.8 metric tons, with some estimates pushing higher, Scotty represents the apex in the size range for the species. Its robust skeleton shows signs of various healed injuries, such as broken ribs and infection, providing raw insights into the life of a massive predator facing the challenges of survival in a harsh prehistoric world. Other noteworthy discoveries include Trix, found in Montana, and Stan, from South Dakota, both substantial specimens contributing critical anatomical data and frequently featured in museum exhibits and scientific literature. Though slightly smaller than Sioux and Scotty, these specimens further demonstrate the variations in size and form that existed within Tyrannosaurus populations. Collectively, these specimens reveal not only extremes in size, but also variation that likely corresponds to differences in age, sex, and individual health. Research indicates that adult T-Rex individuals could range in length from about 11 to 13 meters, 36 to 43 feet, with substantial differences in weight, influenced by robustness and body condition. Beyond mere measurements, the study of these giants enriches understanding of growth rates, illustrating that T-Rex went through an adolescent growth spurt during its teenage years, rapidly gaining the bulk and power characteristic of a top predator. Bone studies also hint at gigantism being a life history strategy, entailing both advantages and costs, including increased resource demand and slower reproductive rates. The largest specimens have also fueled popular fascination and scientific debates, sometimes sparking questions about how large T-Rex could truly grow and what limits evolutionary and biomechanical factors imposed. Advanced imaging, biomechanical modeling, and even forensic techniques continue to refine our picture, revealing insights into walking speeds, bite forces, and muscle dynamics of these titans. In conclusion, Scotty, Sioux, and their counterparts are not just fossilized remains, but monumental chapters in the epic of Tyrannosaurus Rex, embodiments of evolutionary prowess and the enduring allure of prehistoric giants. Their study continues to push the boundaries of paleontological knowledge, bridging the gap between myth and science as we strive to measure the legend itself. Our next exploration will compare these super predators, delving into their skulls, teeth, and bite forces to unlock the secrets of their killing power, a true testament to their reign as the mightiest carnivores in Earth's history. Comparing the super predators of the Mesozoic, those colossal carnivorous dinosaurs that dominated their ecosystems, requires a close examination of three key anatomical and functional traits: their skull morphology, teeth design, and bite force. These factors not only define their hunting capabilities, but also reveal evolutionary adaptations that shaped their ecological roles and competitive interactions. Through detailed analysis, paleontologists have uncovered fascinating distinctions among species like Tyrannosaurus rex, Giganotosaurus, Spinosaurus, and Carcharodontosaurus that illuminate how each mastered survival in its unique environment. The skull architecture of these giant predators was a marvel of evolutionary engineering, balancing power, weight, and function. T-Rex, for example, possessed an immense, robust skull up to 1.5 meters long, characterized by thick, dense bones built to withstand extreme stresses. Its wide jaw and deep snout created a crushing powerhouse optimized for delivering bone-breaking bites. Contrast this with Giganotosaurus and its close relative Carcharodontosaurus, whose heads were generally longer and narrower, somewhat lighter in construction, but outfitted with blade-like teeth perfect for slicing through flesh rather than crushing bone. Spinosaurus presents a strikingly different skull design, with a long, narrow, crocodile-like snout filled with conical, unserrated teeth, an adaptation indicating specialization in catching slippery aquatic prey rather than tearing through tough terrestrial flesh. The anatomy of its jaws suggests swift snapping motions, whereas the more robust skulls of T-Rex and Carcharodontosaurids permitted more forceful bites. Teeth morphology further distinguishes these super predators. Tyrannosaurus rex boasted thick, banana-shaped teeth with serrated edges, sometimes over 30 centimeters long, ideal for biting through bone and muscle alike. These teeth were continuously replaced throughout its life, ensuring a lethal arsenal. In contrast, Giganotosaurus and Carcharodontosaurus had long, blade-shaped, sharply serrated teeth, enabling efficient slicing, akin to the serrated teeth of a great white shark. Not optimized to crush bone, but perfect for cutting large slabs of flesh. This blade-like dentition accounts for their scientific name, meaning shark-toothed lizards. Spinosaurus's teeth are slender and conical without serrations, reflecting its piscivorous diet and reducing drag when snapping at fish underwater. This dental specialization emphasizes ecological partitioning among large theropods, helping reduce direct competition by targeting different prey types. Perhaps the most awe-inspiring metric in comparing these dinosaurs is bite force. Through biomechanical models incorporating skull shape, muscle attachments, and jaw leverage, scientists estimate the bite force of a mature Tyrannosaurus rex to be among the strongest of any known terrestrial predator, up to 57,000 newtons, or roughly 6 tons of force. This crushing power allowed T-Rex to pulverize bones and access marrow, an energy-rich resource inaccessible to less powerful predators. By comparison, the bite forces of Giganotosaurus and Carcharodontosaurus are believed to have been somewhat lower, emphasizing slicing over crushing. Their lightly built skulls and sharper blade-like teeth suggest their hunting strategy focused on slashing large wounds to incapacitate prey rather than sheer bone crushing. The bite force of Spinosaurus is less well understood, but is thought to have been weaker compared to T-Rex, consistent with its adaptation to catching fish and smaller aquatic prey, where finesse and rapid jaw closure matter more than brute strength. These differences in anatomy and bite force also influenced their likely hunting strategies. T-Rex, with immense power and bone-crushing ability, could take down heavily armored or massive prey such as hadrosaurs and ceratopsians. Giganotosaurus and relatives likely targeted enormous sauropods by inflicting debilitating slashes to blood vessels and soft tissues, weakening prey over time. Spinosaurus, uniquely semi-aquatic, specialized in hunting fish and aquatic reptiles, potentially ambushing from water or shoreline. In summary, the nuanced differences in skull shape, teeth, and bite force among the Mesozoic's superpredators underscore the fascinating variety of evolutionary paths leading to apex predation. Each species crafted a lethal design optimized for its environment, prey preferences, and competition, providing a window into how nature crafted giants not just of size, but of specialized power and capability. As we continue, we will explore the unique hunting strategies and competitive advantages these titanic predators wielded, painting a dynamic picture of the Mesozoic's most formidable hunters in action. In the vast and diverse landscapes of the Mesozoic era, carnivorous dinosaurs evolved a stunning array of hunting strategies and unique adaptations, enabling them to occupy apex predator roles across a myriad of ecosystems. While size and strength are often the first marvels that come to mind when picturing these prehistoric giants, it was the intricate combination of anatomical specializations, behavioral strategies, and ecological innovations that truly forged competitive advantages. These adaptations dictated not only how these predators caught their prey, but also how they coexisted, competed, and thrived in environments dominated by immense herbivores and rival carnivores. One of the earliest and most fundamental advantages was locomotion. Agile predators like Allosaurus utilized a combination of strong hind limbs, flexible wrists, and balanced bodies, facilitating swift and maneuverable chases. Their relatively long forelimbs armed with sharp claws played a crucial role in grappling prey after capture. In contrast, the later tyrannosaurids, including Tyrannosaurus rex, sacrificed forelimb length but compensated with incredible jaw strength and bite force, relying primarily on their massive skulls and powerful neck muscles to deliver devastating killing blows. This trade-off illustrates divergent evolutionary paths influenced by prey availability and ecological pressures. Hunting strategies also varied dramatically. Several large theropods, such as Carcharodontosaurus and Giganotosaurus, exhibited anatomical traits suggestive of ambush or burst speed tactics. With long, powerful legs and streamlined bodies, these dinosaurs could close in on large sauropods before delivering precise, slashing bites with serrated teeth designed to inflict deep wounds. It is speculated that they might have used stamina wisely, relying on short, intense chases rather than prolonged pursuits, wearing down prey through successive attacks. Another fascinating adaptation is evidenced in Spinosaurus, the semi-aquatic river monster. Unlike its terrestrial counterparts, Spinosaurus exploited aquatic environments, using its crocodile-like snout, conical teeth, and impressive swimming adaptations, stout limbs, and a fin-like tail, to catch fish and aquatic reptiles. This specialization reduced direct competition with other superpredators and allowed Spinosaurus to carve out a distinctive hunting niche, effectively blending predation in both water and land environments. Social hunting might have also conferred competitive advantages. The discovery of multiple Mapusaurus individuals in a single bone bed hints at possible pack hunting behavior, which would have been revolutionary for such large theropods. Coordinated group hunting could have enabled these giants to tackle prey larger than themselves, increasing hunting success rates and allowing them to exploit the abundant titanosaurs feasting the late Cretaceous landscapes. Sensory adaptations provided further edge. Tyrannosaurids displayed pronounced binocular vision and acute senses of smell, qualities linked to advanced predatory behaviors such as stalking and locating prey over long distances. These heightened senses may have also played roles in social interaction, territorial behavior, or even parental care, indicating a complex behavioral repertoire. Feeding mechanics reveal another layer of specialization. For example, While tyrannosaurids focused on bone-crushing power with thick teeth and strong jaws, the carcharodontosaurids' serrated, blade-like teeth suggest a strategy reliant on delivering deep lacerations rather than opening bone. These distinct dental adaptations reflect divergent ecological roles and prey preferences, minimizing overlap and competition. Furthermore, many large carnivores adapted to their environments through niche partitioning, allowing multiple large predators to coexist. Differences in preferred prey species, hunting habitats, and temporal activity patterns likely reduced direct competition. For instance, while Spinosaurus targeted aquatic and semi-aquatic prey, Giganotosaurus and Mesozoic specialized in terrestrial megaherbivores, and tyrannosaurids hunted a diverse range of herbivores, including hadrosaurs and ceratopsians. Behavioral adaptations may have included territoriality, seasonal migrations following prey, and possibly parental care, suggested by fossil evidence of juvenile dinosaurs associated with adult remains. These strategies could have increased survival rates, improved resource acquisition, and reinforced social bonds. In summary, the unique hunting strategies and competitive advantages of the Mesozoic superpredators were multifaceted and dynamic. From physical adaptations like limb structure, jaw mechanics, and teeth morphology to behavioral traits such as group hunting, sensory enhancements, and ecological specialization. These predators evolved intricate solutions to the challenges of survival. Their stories underscore that being the biggest meant not only having size, but also possessing specialized tools and behaviors fine-tuned to their environments. As we delve next into fossil evidence, trackways, skeletons, and the controversies that challenge our understanding, we will see how these anatomical and behavioral clues are pieced together to reconstruct the lives of these extraordinary predators, moving ever closer to truly knowing the giants that once roamed Earth's ancient landscapes. Fossil evidence stands as the bedrock of our understanding of the giant carnivorous dinosaurs that once ruled prehistoric landscapes. Through an extraordinary series of clues preserved in stone, trackways etched into ancient mud, nearly complete skeletons gradually uncovered from the earth, and sometimes enigmatic fragments, paleontologists reconstruct the lives, behaviors, and environments of these titanic predators. Yet, this evidence does not always present a straightforward narrative. It is riddled with controversies, debates, and reinterpretations that highlight the complexities and evolving nature of paleontological science. One of the most compelling forms of fossil evidence is dinosaur trackways, fossilized footprints that provide a direct window into the movement, gait, and behavior of these creatures. Trackways attributed to large theropods reveal stride length, walking speed, and even patterns suggestive of group behavior. For instance, multiple parallel trackways of large carnivores found in certain deposits have spawned hypotheses of pack hunting, or at least social interaction. Though interpreting behavior strictly from footprints requires caution, trackways also hint at the size and weight of the track makers. Deeper and broader prints suggest heavier animals, while stride length correlates with leg length and, by extension, total body size. In some cases, trackways unfold dramatic scenes. A series of prints abruptly halt near fossilized remains of prey species, suggesting successful hunts or scavenging events. Such trace fossils complement skeletal remains by capturing moments in time impossible to glean from bones alone. Skeletal fossils, by contrast, offer a detailed anatomical record. Over the past 2 centuries, discoveries of dinosaur skeletons, from fragmented bones to almost perfectly articulated specimens, have charted the rise and reign of giant carnivores. Specimens like Sue and Scotty provide comprehensive data on bone structure, musculature reconstructions, and even evidence of injuries or disease. Through these remains, scientists deciphered growth rates, sexual dimorphism, and even aspects of behavior. However, fossil skeletons often present puzzles riddled with incompleteness and taphonomic distortion. Many specimens are missing critical elements. This scarcity leads paleontologists to extrapolate from related species or more complete finds, sometimes leading to differing interpretations of size or morphology. Additionally, the fossilization process can deform bones or displace them, complicating efforts to create accurate reconstructions. Fragmentary remains have also sparked considerable debate. Certain partial fossils once heralded as evidence for record-breaking sizes have been reanalyzed, sometimes shrinking estimates or reassigning fossils to different species. For example, interpretations of Spinosaurus's size and aquatic adaptations shifted dramatically after new finds and refined analyses, underscoring how new evidence can overturn long-standing views. Controversies also arise around classification and species delimitation, as morphological variations within fossils can blur boundaries between species, or conversely, distinct species may be lumped together. The field constantly grapples with these challenges, applying rigorous statistical and comparative techniques to assign fossils accurately. Adding to the complexity, new technologies like CT scanning, 3D modeling, and isotopic analysis have revolutionized fossil study, sometimes affirming, sometimes challenging previous interpretations. For instance, detailed scans of skull cavities shed light on sensory capabilities, while bone histology reveals growth and age patterns. Fossil evidence, with all its power and limitation, weaves a rich, though sometimes fragmented, tapestry of the prehistoric world. It tells stories of ancient landscapes, predator-prey dynamics, evolutionary experimentation, and the very lives of the giants themselves. Yet, it remains an ever-unfolding detective story, where each new bone or footprint might rewrite a chapter, challenge assumptions, or deepen our wonder. As the journey continues, insights from paleo-environmental studies illuminate how geography and climate influenced dinosaur gigantism, leading to our next discussion about the interplay between ancient worlds and evolutionary magnitude. Understanding the tremendous size of many carnivorous dinosaurs requires an appreciation of the paleo-environmental contexts in which they lived. Geography, climate, and ecological conditions formed a complex web of influences that shaped the evolutionary trajectory toward gigantism in these ancient predators. Paleo-environments, ancient habitats preserved through geological and fossil evidence, reveal how factors such as land mass configurations, resource availability, and climate played pivotal roles in enabling and sustaining the enormous sizes these creatures achieved. During the Mesozoic era, Earth's continents were not positioned as they are today. The supercontinent Pangaea gradually fragmented, beginning in the late Triassic and continuing through the Jurassic and Cretaceous periods. This breakup led to the formation of isolated landmasses, creating distinct geographic regions that promoted speciation and allowed disparate dinosaur faunas to evolve independently. For instance, North America, South America, Africa, and Eurasia developed unique ecosystems with differing sets of predators and prey, each influenced heavily by local climate and habitat structure. In areas where lush vegetation and vast herbivore populations abounded, such as the floodplains of North America's Morrison Formation or the rich Cretaceous river systems of South America and Africa, large carnivorous dinosaurs found ample food sources. The availability of massive sauropods and herds of ornithopods provided the caloric intake necessary to support and select for larger body sizes. Thus, the abundance and size of prey animals effectively set an upper ecological limit and developmental pressure for carnivore gigantism. Climate factors also had significant impacts. The generally warmer global climate of the Mesozoic, with higher atmospheric carbon dioxide and no polar ice caps, supported year-round plant growth even at high latitudes, creating expansive and productive ecosystems. Stable temperatures and plentiful rainfall fostered dense forests and wetlands, which in turn sustained diverse herbivore populations, the primary food source for large carnivores. Additionally, warmer climate may have influenced metabolic rates and growth patterns in dinosaurs, potentially facilitating the biological capacity for large size. Geographic isolation sometimes led to unique evolutionary experiments in size and form. For example, the insular environments had different selection pressures than vast continental floodplains, sometimes favoring dwarfism or smaller body sizes. Conversely, expansive contiguous habitats, such as those found in Cretaceous South America, provided the space and resources for predators like Giganotosaurus and Mapusaurus to achieve giant proportions. Other geological factors, such as volcanic activity and fluctuating sea levels, periodically reshaped paleo-environments, driving both adaptation and extinction. Volcanic ash deposits contributed to soil fertility, boosting vegetation growth, while shifting coastlines created new ecological niches or fragmented populations, influencing evolutionary pathways. Oxygen concentrations during the Mesozoic also fluctuated and may have influenced physiology. High oxygen levels can support larger body sizes by improving aerobic capacity. While this remains a complex and debated subject, it is one aspect of Earth's changing atmosphere that likely interacted with biotic and abiotic factors to shape dinosaur gigantism. In summary, the geography and paleo-environmental landscape of the Mesozoic were active forces shaping the size and diversity of carnivorous dinosaurs. The interplay of continental configuration, climate stability, abundant resources, and ecological opportunity created evolutionary fertile ground for the development of the largest terrestrial predators known to science. As we move forward, we will explore the evolutionary pressures and benefits driving gigantism and how these immense creatures balanced the costs and gains of their enormous size within their dynamic world. The phenomenon of gigantism in carnivorous dinosaurs is a remarkable evolutionary story, one that reflects a complex interplay of environmental pressures, biological opportunities, and adaptive advantages. Over millions of years, natural selection favored ever larger body sizes among some predatory lineages, resulting in monsters like Tyrannosaurus rex, Giganotosaurus, and Spinosaurus. But why? What drove these predators to grow so immense? And what benefits did such size confer, balanced against the inherent costs? Understanding these questions sheds light on the evolutionary dynamics that shaped the Mesozoic's giant carnivores. A primary evolutionary pressure encouraging gigantism was ecological opportunity. In ecosystems flourishing with abundant megaherbivores, massive sauropods, armored ankylosaurs, and diverse ornithopods, there arose a niche for predators capable of hunting such prey. Larger body size enabled dinosaurs to tackle these oversized herbivores, overpowering them with strength and leverage that smaller predators simply could not match. Moreover, a large predator could deter competitors and scavengers by intimidating displays and sheer force. Size also correlates with metabolic and energetic efficiency. While maintaining a massive body demands great resource intake, larger animals have lower relative surface area to volume ratios, reducing heat loss and improving energy conservation. This physiological trend may have let giant carnivores inhabit diverse climates and maintain endurance during hunts. Furthermore, increased size generally grants longer stride length and enhanced locomotion capabilities, empowering predators to cover greater distances or close in swiftly on prey. Gigantism likely conferred defensive advantages as well. A larger, heavily built carnivore was less vulnerable to attack or injury from struggling prey or rival predators. It also likely lowered the risk of predation for juveniles growing into adulthood, increasing survival rates within populations. Beyond physical power, size projects social dominance. Large individuals could assert territorial control and access to mates, further reinforcing evolutionary success. However, the evolution of gigantic size entailed significant trade-offs. Large body mass requires vast quantities of food, making these predators vulnerable to fluctuations in prey populations or environmental disruptions. Extended growth periods meant these dinosaurs took years, often decades, to reach full size, exposing them to prolonged juvenile risks. Additionally, large size could limit maneuverability or speed compared to smaller, more agile predators. Another evolutionary constraint involved skeletal and muscular adaptations to support massive structures without sacrificing mobility, a biomechanical challenge met by thick bones, specialized joint structures, and powerful muscles. Breathing and circulation also had to evolve to satisfy the oxygen and nutrient demands of a colossal frame. Evolutionary pressures shaping gigantism also intersected with paleo-environmental factors. Warmer climates, high productivity ecosystems, and stable food webs favored large herbivore populations that, in turn, supported megacarnivores. Geographic isolation on landmasses like South America and Africa enhanced divergent evolutionary pathways, sometimes culminating in unique gigantism events. Ultimately, the rise of gigantic carnivores exemplifies an evolutionary arms race. Herbivores evolved gigantism and defenses in response to predation, while predators escalated size and power to overcome these challenges. This reciprocal dynamic fostered specialization, diversity, and complexity within Mesozoic ecosystems. In summary, gigantism among carnivorous dinosaurs emerged from a blend of factors: ecological opportunity to exploit large prey, physiological and biomechanical advantages, and the evolutionary push to dominate ecological niches. This gigantism came with costs and constraints, but often conferred survival benefits significant enough to drive the evolution of some of the largest terrestrial predators ever known. Continuing on, we will explore some of the ongoing debates in paleontology, sparked by new discoveries and reinterpretations, highlighting how science continually refines our understanding of these giants' biology and history. Paleontology is a dynamic and continually evolving science, and nowhere is this more evident than in the field of dinosaur research. The study of the biggest carnivorous dinosaurs has been punctuated by waves of exciting new discoveries and reinterpretations that frequently challenge long-held ideas. These ongoing debates highlight not only the scientific rigor inherent in the discipline, but also the deep mysteries that still surround these prehistoric giants. One of the most significant sources of debate arises when new fossil finds provide fresh anatomical details that either confirm or upend previous reconstructions. For instance, the discovery of more complete skulls and limb fossils from Carcharodontosaurids and Spinosaurids in recent decades has dramatically reshaped our understanding of their size, posture, and lifestyle. Spinosaurus, once depicted as a typical bipedal theropod, is now widely recognized to have possessed unique semi-aquatic adaptations, thanks largely to new fossil evidence revealing paddle-like tails and limb proportions conducive to swimming. This paradigm shift has prompted reassessments of its ecological role and even its position in the theropod family tree. Similarly, the intensive study of Asian tyrannosaurids such as Allosaurus and Torvosaurus through new finds has enriched debates over phylogeny and biogeographical dispersal, illustrating how isolated populations adapted differently from their North American counterparts. These data drive discussions about continental connections, migration patterns, and evolutionary timing during the late Cretaceous. Re-examination of well-known specimens has also sparked controversy. For instance, debates continue regarding the exact size and mass of the largest T-Rex individuals. Variability in methods for estimating body mass, ranging from volumetric modeling to scaling based on limb bone circumference, can lead to differing conclusions, sometimes igniting vigorous discussions about the maximum limits of dinosaur gigantism. Moreover, interpretations of dinosaur behavior based on bone pathology or nest site discoveries provoke questions about social structures, parental care, and life history traits. Taxonomic debates remain intense as well. Fragmentary remains spur disagreements over whether they represent new species, juvenile forms of known species, or merely individual variation within a species. An example includes the reclassification controversies surrounding Nanotyrannus, which some argue is a distinct genus, while others view it as simply a juvenile T-Rex. Such taxonomic uncertainties affect interpretations of dinosaur diversity and evolutionary pathways. Additionally, new dating techniques sometimes lead to revisions of the ages of fossil-bearing strata, which in turn affect understanding of species coexistence and ecological succession. These temporal shifts can alter hypotheses about competition and niche occupation among large carnivores. The discovery of trackways and nesting sites has fueled further debates by offering insights into behavior and reproductive biology unknown from bones alone. Yet interpreting such indirect evidence requires careful inference, and paleontologists often differ on their implications for group behavior, migration, or growth dynamics. Emerging technologies, such as high-resolution CT scanning, isotopic analysis, and biomechanical simulation, are revolutionizing paleontology, sometimes confirming decades-old theories, but also unearthing surprising new findings. For example, biomechanical models refine bite force estimates or locomotion capabilities, while isotopic data inform diet and habitat use. These innovations often propel fresh debates as prior assumptions must be re-evaluated in light of more precise data. In essence, the debates in paleontology represent the vibrant and self-correcting nature of science, where new evidence continually refines our understanding. They reveal a picture of giant carnivorous dinosaurs that is far from static or settled, but alive with new complexity and nuance. For researchers and enthusiasts alike, this ongoing dialogue fuels curiosity and ensures that the story of the biggest predators remains as thrilling as their ancient deeds. Looking ahead, as we explore cinematic giants, we will witness how popular culture has interpreted and sometimes sensationalized these debates, shaping public perceptions that both aid and complicate the scientific narrative. Cinema has played a profound role in shaping popular perceptions of giant carnivorous dinosaurs, often blending science with imagination to create iconic, larger-than-life creatures that captivate audiences worldwide. From the earliest depictions of dinosaurs in silent films to today's hyper-realistic CGI spectacles, movies have not only popularized prehistoric giants, but also influenced how the public, and even scientists, imagine these ancient predators. One of the landmark moments in cinematic dinosaur portrayal came with the release of Steven Spielberg's Jurassic Park in 1993. It revolutionized dinosaur depiction with groundbreaking visual effects that brought Tyrannosaurus Rex and other dinosaurs to vibrant life. The imposing T-Rex, portrayed with a perfect blend of power, agility, and menace, instantly became a pop culture icon, deeply embedding an image of the Tyrant King as the epitome of prehistoric terror. This influential portrayal, while faithful to some scientific understandings at the time, also introduced dramatic exaggerations for suspense, such as heightened speed and senses. However, cinematic giants sometimes perpetuate misconceptions or overlook subtleties discovered through paleontological research. For instance, earlier films often depicted dinosaurs as slow, lumbering reptiles, whereas modern science reveals many theropods as agile, sometimes covered in feathers, exhibiting complex behaviors. Spinosaurus, featured in recent adaptations, is often dramatized with oversized sails or exaggerated semi-aquatic abilities, reflecting ongoing scientific debates and creative license. Moreover, movies tend to focus on the most fearsome, massive predators, reinforcing their image as the ultimate killers. While this emphasis has popular appeal, it can overshadow the rich diversity of carnivorous dinosaurs, from smaller pack-hunting species to those with specialized ecological roles. Sometimes, the mythical aura surrounding these giants eclipses their nuanced biology and paleobiology. Despite these dramatizations, cinematic giants have an undeniable educational impact. They spark widespread interest in paleontology and natural history, motivating new generations to explore the science deeper. Museums and educators often leverage popular film imagery as gateways to introduce factual concepts, correction of myths, and recent discoveries. The influence of film also fuels ongoing dialogue between scientists and media creators, encouraging more accurate and updated representations. Recent movies increasingly endeavor to portray feathers, appropriate behaviors, and ecological contexts, reflecting the evolving nature of dinosaur science. In summary, cinematic portrayals of giant carnivorous dinosaurs have profoundly shaped cultural perceptions, blending myth and reality in ways both inspiring and challenging. They serve as a testament to the enduring fascination these giants hold and the powerful role storytelling plays in connecting ancient life to modern audiences. Our journey now leads to examining the end of these colossal predators and their legacies, where science confronts extinction and the enduring threads that link ancient theropods to today's avian descendants. The end of the giant carnivorous dinosaurs marks a poignant chapter in the history of life on Earth, a moment when some of the most formidable predators ever to roam the planet disappeared from the fossil record. This extinction occurred at the close of the Cretaceous period, approximately 66 million years ago, during one of the most profound mass extinctions in Earth's history. Commonly attributed to a catastrophic asteroid impact along with rampant volcanic activity and environmental upheavals, this event, known as the Cretaceous Paleogene (KPG) extinction, brought the era of the gigantic theropods to an abrupt conclusion. The mechanics of extinction are complex. The asteroid impact in present-day Chicxulub, Mexico, unleashed an unimaginable torrent of energy, ejecting vast amounts of dust and aerosols into the atmosphere. This led to a prolonged impact winter, causing drastic cooling, darkness, and disruption of photosynthesis at the base of the food chain. Concurrently, large-scale volcanic eruptions in the Deccan Traps released massive greenhouse gases, fueling climate instability. These combined stresses decimated plant life and herbivorous populations, collapsing ecosystems. Without sufficient prey, carnivorous giants struggled to survive. Fossil evidence indicates that, despite their prowess, large carnivorous dinosaurs could not withstand these rapid environmental changes. Their large size and high energy demands, which had once been evolutionary advantages, became liabilities, making survival in resource-scarce conditions more difficult than for smaller or more adaptable species. However, the legacy of these giants did not vanish entirely. Birds, the modern descendants of small theropod dinosaurs, survived the extinction and carry forward the evolutionary heritage of their mighty ancestors. Features such as feathers, hollow bones, and keen sensory systems are living links to the theropods, bridging the gap between the Mesozoic giants and today's avian diversity. Moreover, the extinction of the large theropods opened ecological niches that mammals and other vertebrates gradually filled, reshaping Earth's terrestrial ecosystems. The memory of these ancient kings lingers not only in the bones and fossils studied by scientists, but also within the cultural imagination, inspiring fiction, art, and deep curiosity about Earth's distant past. The end of the giants underscores nature's profound cycles of emergence, dominance, decline, and rebirth. Their extinction set the stage for new evolutionary stories and continues to remind us of the fragile balance that sustains life. Looking forward, the final chapters of our journey will explore modern descendants and how the remarkable survival of theropod traits in birds connects us directly to these prehistoric titans, as well as the thrilling future of paleontology with new discoveries still waiting to be unearthed. Modern birds stand as living testaments to the ancient legacy of theropod dinosaurs, bridging a profound evolutionary gap that spans over 65 million years. While the colossal carnivorous dinosaurs we have explored vanished during the catastrophic mass extinction at the end of the Cretaceous, their lineage continued, giving rise to the magnificent diversity of bird species we see today. This remarkable survival and transformation offer compelling insights into theropod biology, behavior, and evolution. The evidence linking birds to theropods is both extensive and multifaceted. Anatomically, birds share numerous skeletal features with their theropod ancestors, including hollow bones, a furcula, wishbone, three-fingered hands, and a similar arrangement of the hip and leg bones. Fossil discoveries of feathered non-avian theropods from the Jurassic and Cretaceous periods, such as Archaeopteryx, Microraptor, and Velociraptor, provide direct proof of the gradual acquisition of avian traits. Feathers, once thought exclusive to birds, are now known to have been widespread among various theropod groups, serving functions that ranged from insulation to display, and possibly even primitive flight. Physiologically, modern birds retain many theropod characteristics related to metabolism and respiration. They possess a highly efficient respiratory system involving air sacs and unidirectional airflow, a trait thought to be inherited from their dinosaurian forebears, facilitating high-energy lifestyles and, for some lineages, powered flight. The genetic and developmental pathways underlying these features also help scientists unravel the evolutionary steps, leading from ground-dwelling dinosaurs to the masters of the skies. Behaviorally, parallels continue. Courtship displays involving feathers, complex vocalizations, nest building, and parental care align with interpretations of theropod behaviors inferred from nesting sites and bone beds. Even social structures and hunting tactics exhibit echoes in certain bird groups, suggesting a continuity of ecological strategies. Understanding birds as modern theropods recontextualizes our perception of the age of dinosaurs, transforming it from a story solely about gigantic reptiles to one of evolutionary continuity. The survival of the theropod lineage through the end Cretaceous mass extinction underlines the adaptability and resilience of this group, highlighting traits such as small size, flight capabilities, dietary flexibility, and sophisticated behaviors that enabled survival amid planetary upheaval. Moreover, bird fossils and recent molecular studies continuously inform dinosaur paleontology, illuminating evolutionary relationships and functional adaptations. Conversely, dinosaurian fossils provide a deep historical framework to appreciate the origins of modern avian diversity. As we explore the modern descendants of these ancient giants, it becomes clear that their influence endures, flying overhead in the form of countless feathered species. This evolutionary legacy is both humbling and inspiring, a vibrant link connecting the prehistoric past to the living present. The story of theropods does not end with extinction. Instead, it thrives in the continuity of life, beckoning us to look skyward and marvel at the lasting impact of Earth's mightiest predators. In our final section, we will look forward, examining what could still be out there in the fossil-rich shadows and how future discoveries may further transform our understanding of these legendary creatures and their world. Despite centuries of fossil hunting and remarkable strides in paleontology, the prehistoric world of giant carnivorous dinosaurs remains only partly illuminated. Vast stretches of Earth's ancient landscapes lie unexplored or underexplored, and new fossil discoveries continue to rewrite our understanding of dinosaur diversity, evolution, and ecology. The future of paleontology promises exciting revelations that could reshape our grasp of these magnificent creatures and their role in Earth's history. Several factors combine to fuel this optimism. First, many regions with rich fossil potential, such as parts of Africa, South America, Asia, and Antarctica, still yield untapped deposits. In these areas, ongoing excavation projects frequently uncover new species, previously unknown skeletons, and invaluable trace fossils, expanding the dinosaurian family tree and revealing unexpected anatomical adaptations. Technological advances profoundly enhance fossil detection and analysis. Remote sensing, ground-penetrating radar, and drone surveys allow identification of promising dig sites in challenging terrains. High-resolution CT scanning and 3D modeling permit detailed virtual reconstructions of fossils without damaging delicate specimens, enabling deeper insights into dinosaur anatomy and function. Molecular paleontology, an emerging field, endeavors to extract biochemical signatures and ancient proteins from fossilized tissues, offering prospects to understand dinosaur physiology, coloration, and phylogeny with unprecedented depth. Although DNA degrades over millions of years, the recovery of structural biomolecules presents tantalizing evidence about life's ancient details. Continued discoveries also challenge and refine long-standing scientific paradigms. For example, new fossils of feathered dinosaurs expand our knowledge of integumentary structures, while unusual theropod specimens reveal unexpected ecological strategies such as herbivory or semi-aquatic lifestyles. Such findings underscore the complexity and adaptability of dinosaur lineages, negating overly simplistic narratives. Interdisciplinary collaborations between paleontology, geology, climatology, and molecular biology enrich interpretations, contextualizing dinosaurs within dynamic Earth systems. This integrated approach aids in reconstructing paleo-environments, migration patterns, and evolutionary pressures that shaped dinosaur gigantism and diversity. Moreover, public engagement and citizen science projects have opened new frontiers for fossil discovery. Enthusiasts and local communities contribute to locating and preserving fossils, accelerating research and education. Looking forward, the horizon of paleontology is vibrant with possibilities. Each new specimen, footprint, or trace element holds the potential to answer long-standing questions and plunge us into fresh mysteries about the mightiest carnivores to have ever walked the earth. In the grand tapestry of life, giant carnivorous dinosaurs, though extinct, continue to inspire wonder, provoke inquiry, and connect us to a deep and fascinating past. The future promises that many more secrets await, buried beneath ancient soils, waiting to be unearthed by generations to come.